And tonight's speaker is, as I said, Yohe, and he is NASA Jet Propulsion Laboratory Solar System Ambassador. You won't be tested on this, so. And he's going to present up-to-date information and images that depict the past, present, and future exploration of our solar system. Thank you very much.
All right. Well, thank you, everybody. Thanks for having me here tonight. Bear with me. I had a little issue earlier on this. Yeah, but hopefully once I get going, sorry, folks. That's the end of the show. No, wait. No. There we go. So my name is Yohe. I'm a volunteer with NASA's Jet Propulsion Laboratory. The Solar System Ambassador Program is a pure volunteer program that's there's several hundred of us across the country. We all do something a little bit different. Some people focus on robotics, some on our pure astronomers who do star parties. What I kind of try to do is pull information from lots of different resources to give you a summary of the exploration we're doing in the solar system. So the presentation you see today is 100% put together by me. So if there's any mistakes, those are mine, not NASA's. And it's all from publicly available resources. I just kind of try to consolidate it for you. So that's my volunteer work. For a living, I work at UW Medicine over at UW Medical Center. I'm in our facilities group as a technology project manager. I work on nurse call deployments for mobile device integrations and mobile asset tracking. I work with Robin, who I used to work with back in our Harrison Medical Center days, and she just recently joined our team and is absolutely critical to what we're doing for nurse call for our patients. So nice to see you guys here. Yeah. So diving right in, and just so you know, I've quite a bit of material to get through. I'm not going to take any questions until the very end, but then for those here, I can stay as long as you're still available. But I have quite a bit to get through. We're going to be taking what I call a hike through the solar system. And one other thing for those online, I'm using my laser pointer. I'll occasionally try to use my mouse to point at things if they're real specific. I won't do that for everything, but you won't get to see the laser pointer. So yeah, so we're going to take a hike through the solar system, starting with the sun, working our way out to the inner planets, the outer planets, and beyond. And just know, we only have this, an hour tonight. There's so many missions out there. For every mission I talk about, there are dozens and dozens and dozens more. I can just give you a little taste. And actually, usually this presentation can be even a little longer. One of my weaknesses is taking things out because there's always so much interesting stuff. So there's some places where I'll kind of fly through some slides. Hopefully, at least they act as a little bit of a teaser for you for things to research more. So we're going to start right with the middle of the solar system, the sun. Our sun is a star, like the other stars in the night sky. Our star is an average size star. There's some way bigger, there's some way smaller, but none closer to us. And we'll talk a little bit more about that in a minute. So kind of stars 101. The way a star forms, and we see this happening all over the cosmos, is you get enough raw material, primarily hydrogen, in one place, and just the raw gravity of it starts to cause this collapsing effect. And eventually, if there's enough, you can get to the point where you start nuclear fusion. And nuclear fusion is where you have two elements merged together, in this case initially, two hydrogen atoms merge and become a helium. And when that happens, and it takes huge pressures for that to happen, a little bit of the mass is lost and it turns into pure energy. So it's like a nuclear fusion bomb going off constantly. And that's how stars work. They're basically these big nuclear fusion engines. As time goes on, other elements form, heavier elements form. Calcium in my teeth, iron in my blood came from inside stars. Stars are element factories. All the elements around you were formed inside stars. And we get to see this happening all over the cosmos. Then, you have the star form out of this big cloud of material, and then what's left can start to coalesce into planets. Of course, we can't see that happen on our own solar system because it happened so long ago, but we do see that happening with star formation or in other spots of the cosmos. And eventually you get planets through a pretty elaborate, complex, long process. So I say our sun is an average sized star. It's still big, it's still really big. 109 times the diameter of the Earth. We're going to talk about some really big distances and sizes today. And we're going to try to wrap our brains around it a little bit. So we're going to build a scale model of the solar system. And to do that, to have something we can talk about in this room, this tennis ball will represent our sun. So if this is the sun, then I'm going to make a model of the Earth, which will be a spit wad. So spit wad, sun. And so we're going tennis ball, spit wad, way too big in this picture. And then, so that's size, but now they're actually 93 million miles apart. On this scale, when I got my tape measure out earlier, that's 22 feet. So I'm going to set my tennis ball. You won't see it again here for a little bit, but I'm going to sit it back here on a table. I'm going to walk across the room 22 feet over to the snack table. And I'm going to put, wow, and I'll put the Earth over there. So that's 22 feet, tennis ball to spit wad, size and distance to scale. There's another feel for you. If that's the orange ball is the sun, that little dot down at the bottom, that's Earth to size without the distance. So obviously the sun very much so dominates our solar system. So the sun gives us lots of great things, right? Heat, light, photosynthesis. We wouldn't be able to be here without the sun. Sun also gives off a lot of particles that don't make it to the Earth because we have an atmosphere and magnetic field. So what we did was we built a spacecraft to go up and try to capture some of those particles and bring them back for study. I say we, you're gonna hear me say we a lot. I've never built a satellite. I don't actually work for NASA. I'm just a volunteer. So when I say we, think of the people doing that. Think of yourselves because you're funding it with your tax dollars. And really almost everything NASA does has international collaboration of some sort. So we here tonight really means humanity. So anytime I say we, just in your mind, replace it with human beings. So we, human beings, built this spacecraft. And Genesis is similar to a lot of the spacecraft we're going to talk about tonight. For one, it's robotic, going further into space than we can send people yet. And just to give you a feeling for the size, it would fit easily, like the core where all the computers and the sampling equipment and the communication equipment would fit up in the front of this room. So kind of picture up in front of the screen. The solar panels extended out would be probably corner to corner of this room, probably a little bit bigger than that. And it all folds up to launch. So kind of gives you a feel for the size. To launch something that size that fits in the room takes a rocket 200 feet high. That spacecraft is stored up in the nose cone, and all the rest of that 20-story rocket is fueled. And it's almost like driving a car and your gas tank is the size of a semi-truck. Yeah. And you need that much fuel because getting into space, we think about going high to get into space, right? But what's even more important is fast. You need to go at least 17,500 miles an hour to get into Earth orbit. So rockets take off and they quickly start to arc over and just to pick up speed. In the United States, we usually launch our rockets from Florida. And the reason for that is all about that speed thing. The Earth rotates once every 24 hours. At the equator, it's 25,000 miles around in circumference. So if you're on the equator, you're already going 1,000 miles an hour in relation to space. So that's that much less fuel your rocket needs, or that much bigger of a payload you can take. Up in Washington here, we're closer up to the North Pole, but we're still going fast. We're going about 600 miles an hour in this room. So if the Earth stopped spinning right now, we would fly out of our seats at 600 miles an hour. It's not going to, but that would be the case. So exploring space is tricky. The Genesis mission was like 99.9% successful. Great rocket launch. The spacecraft operated fantastically in space for years. It collected its samples, brought them back to Earth. The heat shield worked great as it came down through, but the parachute didn't open. And the parachute didn't open because one technician had one component in upside down that didn't sense the gravity, right? But we all know that there wasn't just that one technician, right? What was the environment? Was there room for collaboration among people? Could people raise their hand and say, hey, I've spotted this issue? I didn't work on that team, but I can tell you and we all do so much. I mean, I work at a hospital. Our attention to detail can be life and death. And that attention to detail And space exploration is super important. So you got to be willing to take risks, but then also sometimes a simple little mistake can really ruin the day. They did manage to extract some information from this, which was pretty miraculous, but it would have been a lot better if it had gently landed on the ground. A mission that's been very successful is SOHO, and it's lasted for decades beyond what it was supposed to. And it's designed to monitor space weather. So when I talk about space weather, the sun, it's our good friend, right? It gives us heat, light, photosynthesis, but it's also a gigantic nuclear fusion bomb going off all the time. And it sends some pretty big stuff our way. There's constant activity on the sun, and some of those solar flares and storms can head towards the Earth and put our satellites at great risk. And now we have so many satellites we count on for internet access, for communications, for weather monitoring, even GPS does more than let you know where you are on your map. GPS is the timing clocks that the entire world's banking system uses. So you could have a solar flare that disrupts all financial markets on the planet. Even on Earth, there can be problems. This was a picture from 1989. And what's missing in the red circle is lights, the lights of Montreal, because a big solar storm hit, blew out transformers, and several million people were in the dark for a long time because of a storm coming from the sun. To give you a feel, we know this is not the scale. This is not to scale distance, but size is. So the Earth. So this is a coronal mass ejection coming off the sun, and when something that big is coming our way, we want to know about it, because there are things we can do, like maybe power down satellites, put them in a safe mode, maybe turn off power grids to be able to be ready for that storm when it hits. It'd be better to, when I was a kid in Pennsylvania, when there were lightning storms, we'd unplug the refrigerator or the TV, because it was before surge protectors and what have you. That way you wouldn't blow up your equipment. Same idea now, just on a global scale. In 1859, there was a really, really big event called the Carrington event. And these were drawings of solar sunspots on the sun, and that was him looking through a telescope with a super good filter. Never ever look at the sun through a telescope or binoculars or anything, or you will go blind. Literally, you will burn your eyes. But if you have the right filter, you can see it. So he sketched these huge features on the sun, and a couple days later, boom, they measured this magnetic field hitting the Earth, and there wasn't a whole lot of electronic communication at the time, but what there was all over the planet was heavily disrupted. Telegraph systems went haywire across the entire planet. If that Carrington event happened today, well, this would probably be a candlelight conversation, because we wouldn't have restored the power grid yet. We just have to talk it through and do it on a whiteboard. We could have trillions of dollars of permanent damage from an event like that. And they're not as rare as we might hope. Just a few years ago, there was a storm that size aimed right at Earth, and we missed it by a week. Zip by. So being ready for these kind of storms is a big deal. So what do you do when you face threats? You got to collect more data so you can know what you're dealing with. The stereo mission used 2 satellites at different angles to use 3D projections of these solar storms as they come through the solar system. This mission also discovered, amazingly, on the sun, there are tsunamis on the surface of the sun. And a tsunami on Earth is, it's a big wave, but not caused by wind, caused by an earthquake or a mudslide, or if you drop a pebble in a bucket of water and you see the ripples, that's a little tsunami you just made. There's no water on the surface of the sun, but there's the plasma, there's hot plasma, and the same kind of effect happens, except on a big scale. You get tsunamis that are about 64,000 miles high. So picture a tsunami coming at you that's several times the height of the Earth. So the sun is a very dynamic place. The Parker Solar Probe is flying closer than we've ever flown before, and it has a very complicated way to get there. What we actually do is we do what's called gravitational assist, and you use the gravity of other planets to speed up, slow down, or redirect your spacecraft. So you have to be really good on the calculations. You have to know years in advance where that spacecraft's going to be, where that planet's going to be, how close you have to be, what angle you have to be at to do your speed up or your slow down. But it's working. And right now, Parker Solar Probe has given us our first pictures from inside the atmosphere of the sun as it flew through. Wow. And here's a picture. This is pretty almost up to date, approximately the last 48 hours of solar activity. And then if you zoom in on this one area here, that's a coronal mass ejection, unlike the ones we've talked about. That's seeing it from a different satellite view too. that happened yesterday, and it's heading our way, and it's not a direct big hit. It's not going to be as big as these other events. These kind of happen somewhat frequently, but the Earth's probably going to be grazed by this on Sunday. Probably enough to knock out some radio communications like in Northern Europe. Probably enough that there are chances of seeing the auroras go up, actually, whenever this is happening. And we'll talk about that in a minute. But yeah, but coronal mass ejection is heading our way right now, and we keep a close eye on them. So now we get to the planets. Mercury is much closer to the sun than the Earth. So not surprisingly, it's way hotter, 332 degrees Fahrenheit, 167 Celsius. This is average temperature, but it's kind of weird. Its average is way out of whack, as a day on Mercury is longer than a year on Mercury. Because a day on Earth is 24 hours, right? How long it takes the Earth to rotate one time. A year on Earth is 365 and a fourth days. How long it takes us to make one orbit around the sun. Well, Mercury orbits around the sun every 88 of our Earth days, but it takes 176 of our Earth days to rotate once. So one side's always really hot, one side's always really cold, and then that shadow just slowly marches across the surface. We sent the Messenger spacecraft and went in and got just amazing maps of the entire surface. And now there's another mission on the way there, which is a joint European-Japanese mission to study Mercury further. And you'll see that's kind of a recurring theme. You know, you go once, and then you almost always come up with more questions than answers. So then you build the next generation of instruments to go answer those questions, and you build on it and build on it. So we just keep learning more and more. And this was its flyby of Mercury very recently, actually, on one of those gravity assists. Now we get out to Venus. So Venus is further from the sun than Mercury. So the scientific community figured it would be cooler, right? Just inherently, but it's not. It's like 3 times as hot. Average temperature, 867 degrees Fahrenheit on Venus. And Venus is almost a duplicate to Earth in size. But the thing that makes it so much hotter, I mean, it's hotter than a pizza oven, is this. It's carbon dioxide. It has a really thick carbon dioxide atmosphere. And this is, and basically this has kind of helped us understand carbon dioxide on Earth too. Just the fundamental nature of the molecule of carbon dioxide traps more heat in than it lets out. And that's just how that works, no matter what the source of the carbon dioxide is. But on Venus, it's gotten really, really hot. Venus has been tricky to explore. Getting down to the surface is tough because that atmosphere is so thick. But then also there's also a huge cloud cover over the planet. And so we sent the Magellan spacecraft, and it used radar, and it did radar mapping of the entire surface of Venus. At one point, we had better maps of Venus than we had of Earth. And then we've used that same technology back here. So, when you get good topographical maps on your Google Maps, a lot of it's building off of that technology. And the Japanese have a spacecraft up there right now collecting more data, and it actually did a test on its way there of a solar sail. So it sent out a sail that actually uses sunlight to push it through space, just like wind pushes a sailboat across Puget Sound. And so far, so good on that experiment. Now we get to Earth, my favorite planet by far. I'm guessing yours too, I would imagine. Some really important things about our planet. One, this. Only place in the solar system where I can take a breath of oxygen-rich air without being inside a spacesuit or a spaceship. Very important for our survival. The other big thing down here at the bottom is our temperature. Average temperature, 59 degrees Fahrenheit. The liquid point of water. All life that we know of so far needs water. Bacteria, alligators, ants, humans, everything needs liquid water to survive. And if we were a little too close to the sun, it'd be too hot. Venus probably has no liquid water anywhere, right? If we're too far away, it can all freeze, like what's happened on Mars. We call it the Goldilocks zone. It's the habitable zone where it's not too hot, not too cold, and we can actually live here. So liquid water is very, very key. We have a magnetic field which helps protect our planet. We're pretty sure that we have still a rotating iron core down inside the planet that causes this big dynamo to happen, right? Leftover heat still from the creation of the Earth. And so that basically gives us force fields. Just like on Star Trek, they have shields. We have shields around our planet. If we didn't, like Mars, we would have lost most of our atmosphere by now from the sun bombarding us all the time. So that shield, though, it does have its weaker points at the poles, and that's how you get auroras. Basically, when you see the northern or southern lights, that's an interaction of solar particles with the atmosphere and with those magnetic fields. And we still don't fully understand them and continue to study them. And who knows, maybe we'll see some here if it stays clear in that CME that's heading our way. That's a light show. The Carrington event in 1859, you could see the auroras in the tropics. The entire planet was aglow with auroras everywhere. There's no photographs of them because it was 1859. There's lots of paintings, but yeah, very huge event. And we monitor our magnetic field on a regular real-time basis because there are fluctuations. It's not an ever-present thing. Sometimes there are holes in the magnetic field that are enough that we have to redirect commercial aircraft around them because their instruments could be disoriented on their flights. We have a whole host of satellites that have studied all aspects of the Earth. Well, not all of it, many aspects of the Earth, of weather, of how waves form. Our most practical real world of benefits of that is now that we are so much better at predicting storm paths and landfalls than we used to be. I mean, you just think how many lives have been saved from what we're able to collect from satellite data. There used to be, well, for hundreds of years, people talked about rogue waves, big 100-foot waves that would come up out of nowhere, and there was anecdotal evidence of it. But then we use satellites, and we can look at all the wave heights of the entire world on a weekly basis. And guess what? About every 2 weeks, somewhere in the world, a 100-foot wave pops up out of a calm ocean. We don't usually hear about it because usually no one's there to see it, but it happens. And some places they kind of know why, have an idea, and some places they have no idea. So, but it's a real phenomenon. It wasn't just sailors coming back with tails. Our ozone layer is something we've monitored with satellites, and the ozone is a very important layer of our atmosphere. And what it really does for us practically is it shields us from ultraviolet radiation. But a few decades ago, we started to realize it was getting thin through both ground and satellite measurements. And there was actually a big hole that was opening up over Antarctica, an ozone hole. And then, so through scientific processes and testing, we figured out that we were the problem. We were emitting things called chlorofluorocarbons, which are refrigerants, and they were also used in aerosols. So in 1989, pretty much most of the countries of the world got together at a big conference in Montreal, Quebec, agreed. They said, hey, we as humans are emitting something into our atmosphere that's hazardous. It's going to be very expensive to get rid of it, but it'll be more expensive if we don't. So over the decades, production has really, really dropped. And there's even signs now that the ozone hole might be healing. So looks like actually countries can all come together and solve a problem that we've started. And I threw this in just because it's a fun picture. This was actually there's about 300 Lego astronauts there and they're suspended from underneath a weather balloon. So they're up at a high altitude weather balloon. And this was like a public outreach thing for kids in the Czech Republic and Slovakia. But I just thought it looked cool because it had the Earth behind it. First satellite ever launched was Sputnik, launched by the Soviet Union in 1957. That kind of kicked off the whole space race, and NASA soon launched our Explorer 1 spacecraft. Everything we've talked about so far has been robotic, but we certainly started sending humans into space. In those days, Yuri Gagarin and Alan Shepard were our first two Americans to launch. And nowadays we see astronauts doing somersaults and stuff in space. And these days that was not happening. These were very cozy spacecraft, right? And even now the Soyuz spacecraft is, I mean, you're in tight, you're ready to go somewhere else. So over the year, when the United States built our space shuttle, which we used for 30 years, 3 decades is our primary way to get to space. And it did amazing things. I mean, it could do construction projects, and it launched satellites and space probes, and it helped build the International Space Station. But still the crew was kind of confined to this smaller cabin area up in the front. And so basically over the years, there's been a need and several have been built, some space stations. And the idea of a space station is you build a laboratory and you leave it up in orbit, and then you use smaller spacecraft to get people to and from it. So it doesn't have to have parachutes and heat shields and all that kind of stuff. So all these space stations built by Russia and the US and some joint efforts, they have since fallen out of orbit. They wear out like all machines do, and they've been replaced with this. This is the International Space Station. By far the largest spacecraft ever made by humans anyhow. So this is just to give you an idea of size. This is where I work over here. That's the Montlake campus of UW Medical Center, and that's Husky Stadium. So it would fit down inside there, about 300 feet long, a couple 100 feet wide, solar panel. So very large spacecraft. Had to be built in pieces because it's just too big to launch all at once. And again, international, built by several different countries. Like Legos. Here I'm talking about Legos again, right? Legos and space just go hand in hand. But that's my Lego space station I have at home. And that's really a good analogy because that's how it was built. And you actually, over time, different pieces of the space station have been moved depending on where it was in its phase of construction or what needed to be put there. So it was very key to build all these pieces to be modular. And there's a Russian main command section. There's a American, European, and Japanese laboratories. There's a Canadian robotic arm. It's a big robotic arm on the top. So clearly just a huge international collaboration. This was the last shuttle launch to the space station in 2011. It was Atlantis. And the shuttle got retired for some good reasons we'll talk about, but it was still very cool to watch it whenever it would come in and dock with the space station. It was an amazing machine. The way the station is built could not have happened without the shuttle. A lot of spacewalks were required. Here we have walks where basically astronauts are in a little mini spacesuit. So they're counting on lots of people to have done things right. It's not just the engineers and the astronauts, it's the electricians, it's the carpenters, it's the plumbers, it's the custodians that kept the clean rooms clean for their oxygen cleansing equipment, the software people, the IT people, the people that stitch the gloves and the suit. It's a vacuum of space out there, and you go from 200 above zero to 200 below zero, depending on if you're in the sun or the shade. So it takes a lot of people to make something like this successful. On this particular spacewalk, they were opening up the windows of the cupola. So the cupola is kind of a bay window in space. So I think it would be kind of cool to float in zero gravity and look straight down 250 miles, zipping along at 17,000 miles an hour. It's a very popular spot. There's a picture taken from the cupola. That was Atlantis going back in for its final landing. That's its plasma trail as it went down through the atmosphere and coming in for a nice safe landing to wrap up the space shuttle program. One of our astronauts was a teacher. She had to wait 20 years before she finally got to fly into space. She was the backup for the Challenger mission, which was an accident back in 1986. She finally got to go. She's a great astronaut, great teacher. But I really want you to focus on her hair on Earth and her hair in space, right? Zero gravity, no up or down. It's fun, but it's complicated. It's kind of funny sometimes. I've seen interviews with astronauts that after they've been like on a long duration mission, 6 or 7 months, they'll just be a day when they drop a glass of milk because they forgot they needed a table, right? Because they were so used to zero gravity, So Velcro is very important in space. Like all astronauts, Barbara had to start as a kid, studying hard and learning things and applying herself. And we've had astronauts come from all kinds of backgrounds. It takes and have all sorts of other opportunities. Charlie Bolden went on to lead the whole agency after being an Air Force pilot and astronaut. This was the most recent recruitment. This is our most recent group of astronauts. And just, NASA just epitomizes it. Diversity is mandatory because otherwise you're not going to have the best of the best. You need the best of the best to be astronauts, and that just inherently results in a pretty diverse team. My hero astronaut is Peggy Whitson. She has spent more time in space, all added up, than any other American astronaut, well over 600 days. And she's now retired from NASA, and as a private citizen, she commanded a private space flight up to the space station recently. So she's still gotten to fly into space. So that's kind of cool. This was just today. Today's the start of a crew rotation on the space station. So I snapped a screenshot when I was getting ready for today. And that was a Soyuz launching from Russia with 2 Russians and 1 American on it. And that's them coming in. And so these are the 10 people. So this picture is like 2 hours old. These are the 10 people on the International Space Station right now, representing the United States, Russia, Denmark, and Japan. In addition to the people that get to go up there, there's a lot of experience, there's still only so much space on the space station, but lots of experiments from more than half of the countries of the world have gotten to send experiments up to the station. And this is everything from working on vaccines to cancer treatments. I've talked to them, there's work being done to see if they can put chemotherapy drugs together in a different way in zero gravity that could effectively, it would eliminate our 8 Southeast infusion unit at the hospital if it worked. So, because instead of sitting for 6 hours getting your treatment, you could just get a shot if this works. I mean, they're not there yet, but there's all kinds of that research happening on the space station. We recycle water, recycle urine and sweat to turn it back into drinking water, and have been able to compact that technology down to very compact to the point where it could be very useful for like emergency responses or rural communities that don't have access to clean water from wells. And talk about recycling. There's a machine I just love is the refabricator, and they've already figured out how to do 3D printing in space. But now what they're actually doing is taking the plastic packaging that they use to keep all the samples safe, and then they can use that as feedstock and they can print things out of it. And then they put it back in and print it again. So I would love the day that this spins down to me having one of these in the kitchen, and I get a box from Amazon and I just dump the plastic peanuts in and I print out a wrench. That would be, and that's literally what they're trying to do. So, and they have fun up there too, right? And you gotta have some espresso too. So they got the space espresso maker, which was a big technological challenge actually. Another cool thing about space station is you can watch it fly over. I have an app on my phone. There's a couple websites you can go to, and it's really cool to see. It's the brightest thing in the sky. And guess what? Tonight I looked at it before we came at 9:05, there's going to be a flight almost directly over Bremerton, and it looks still clear out. And you have to get out there in time and just cast a wide look for it. And it'll be kind of heading from, west to east. But you'll see this bright dot that's like one of the brightest things in the sky moving like nothing else. So I highly recommend you go out and look at the space station tonight. Kind of cool to look up there and say, hey, I know there's 10 people up there and it's going 17,000 miles an hour. Wow. And the view from the space station is, you get pictures you just don't get anywhere else. Thunderstorms over Texas and flying through the auroras. And these aren't the only people in space. There's a Chinese space station now too, and there's 3 Chinese astronauts up there. So there's a total of 13 people in space right now. After NASA retired the shuttle, they really started to rely on private companies to try to reduce the cost of getting more competition and more innovation in, and getting more cargo up and some redundancy. And that's really worked out pretty well. This was some rollout solar arrays going up on a SpaceX cargo mission recently. But even though we've had the cargo going up and down for a decade after the shuttle, we were 100% dependent on the Russians to get people up to the space station, because it's a joint project with us. But NASA kind of used the same idea of putting out to bid, let's get some American innovation here and build some alternatives. And sure enough, Boeing and SpaceX got contracts. SpaceX has now taken dozens of people to and from the space station. More affordably, yet still safely than NASA was ever able to. Boeing's not quite there yet, but hopefully here in the next year, they'll have a redundancy. So we'll have 2 different ways to launch astronauts. But we still share rides with the Russians and the Russians with us, that we always have a way to get both of our countries represented on the station. And that's led to innovations that, this would have been, NASA's very innovative, but I don't think they would have invented Buck Rogers' rocket ship landing styles. This happens all the time. SpaceX has done this like 100 times now. They reuse their boosters, fly them again. We fly astronauts on them. So if you had sent me a picture of this 10 years ago, I would have told you you were nuts. There's no way anyone can do that, but they do it all the time now. And there's a whole other private sector. There's lots of other companies doing small satellite launches, suborbital. It's just the whole industry has really opened up quite a bit. And the space station won't last forever. So they're already working on plans, again, to try to have commercial companies come in and build the next space stations. And then NASA and other countries would be customers. They would basically buy time in the laboratory. So they're really trying to build that, because NASA wants to put more of its effort towards now, kind of at some point sort of hand off low Earth orbit operations to all these private sectors and having an economy there. And NASA's working on going to the moon. So that takes a lot of work. It takes a lot of development of new spacecraft and rockets, This is the Space Launch System. This is the primary rocket NASA's using. And just to give you a feel for how big a rocket you need, if you've been out to Fort Worden up in Port Townsend, this is Fort Worden State Park. So I kind of put a representation there at the state park, like where you have all the RVs. The top of it would be above the bluff looking down in. So yeah, very big rocket. And why do you need such a big rocket? Because the moon is really far away. The highest the space shuttle could go was 350 miles. The moon is 239,000 miles away. So it just takes more oomph to get all your stuff there that you need. So that's what we're working on. So the moon is that next big destination. The moon's very important to us in many ways we might not think about all the time. I mean, one is our tides. So the moon and the earth are kind of locked in this tidal dance that causes the oceans to slosh in a big way around the whole planet. We see that every day in Bremerton, right? High and low tides. That's the moon. But the reason that we have such predictability is we're pretty sure the more and more evidence comes out that probably the way the moon formed was in the early Earth. Earth probably got whacked by another planet like the size of Mars, but at an angle. We've done all sorts of computer simulations on this to see, what makes sense. Which would have put us at this 23-degree tilt. The Earth is at this 23-degree tilt in its orbit around the sun, and the moon is locked in with that. And so that's really important for all kinds of reasons. It's important because it stays that way as we orbit around the sun, and that's what gives us seasons. So if we didn't have that 23-degree tilt and that moon locked in that orbit with us, we wouldn't have spring, winter, summer, and fall. And in fact, it'd be even more chaotic. We'd probably wobble a lot over time. And so you'd have points when the North Pole was pointed straight at the sun, it would just melt completely. It would be almost impossible for life to keep surviving without our moon. Here's an actual photograph from the OSIRIS-REx spacecraft of the Earth and the moon in the same frame, which I thought was kind of cool. Lots of missions went to the moon in the 60s. Sample return missions and landers and rovers as part of the big space race. And then we landed humans on the moon in the Apollo program between 1969 and 72. 6 missions landed on the moon with a total of 12 astronauts. And it was amazing, and it was stunningly successful, but it was brief. It was this huge effort, and all this resources went into it, and then all that hardware was taken apart. And we went on to build the space shuttle, and there's still research being learned from what happened during that brief Apollo period, but it was kind of a flash in the pan. So, kind of there's the saying of if you want to go fast, go alone. If you want to go far, go together. And so now that's what we're doing. We're working with many other countries to work on building a space station out by the moon as a base camp for further exploration, as a stepping stone. We are using some of that commercial, what we've learned about saving money, trying to use commercial providers to provide landers under huge supervision. So this, in theory, will be what our first landing ship's going to look like from SpaceX, and they've actually done some testing on that already. And we're also working with lots of other partners on, can we hire somebody to come provide the power? That way NASA doesn't have to invent everything from scratch. Let's put it out there to bid. Let's see who comes up with the most innovative idea and have them share some of the cost risk. So the Artemis in mythology is the twin sister of Apollo. So that's why this program is called Artemis. And again, and it's expanded. Rather than just the United States trying to put boots on the moon, there's now a whole group. The Artemis Accords have been signed by many countries, and there's a lot of principles that go along with it. It's not just saying, hey, we want to go to the moon. It's talking about safety. It's talking about respecting heritage sites like the Apollo 11 landing site, talking about having common interoperability of common docking ports so we could go rescue each other if we have to. So there's this whole effort, and more countries are coming on board under US leadership, NASA leadership. Right now on the moon, China has an active rover. They have not signed the Artemis Accords. They are not part of that, not at this stage anyhow. But India has, and India just landed a rover, the first rover of any country, or the first lander or rover of any country to land near the South Pole of the moon. So that's been very successful. And then NASA's first big mission for the Artemis program was Artemis 1. It was a test mission. They launched that big rocket, sent our spacecraft out around the moon. Didn't have humans on board, no human astronauts, It did have a couple passengers. Snoopy went to the moon, so Snoopy got to float around the moon. And the European Space Agency built the service module that runs the spacecraft, so they got to send Shaun the sheep and a couple Legos too. So we have some people who've gotten to go out there. And it was a very successful mission, and they're collecting all the data from it now. The next one, in about a year, we'll have people on board. And so there'll be 1 Canadian and 3 Americans going further than human beings have ever gone. They won't land on this next trip, but they'll be going out on a big, deep orbit around the moon. And you just get a perspective of the moon from the Earth, or the Earth from the moon, that you just don't get from anywhere else. That was taken on Apollo 8 by Bill Landers, who lives up on Orcas Island, actually. And big exciting thing happening here on October 4th with the sun and the moon is that annular eclipse. So that's not quite like the full one we had a couple years ago. But if you're in this path, you'll be able to see it'll look like a donut during that time. But then even up here in this map, and if you go out to a Great American Eclipse, there's lots of resources for this. We'll have about a 70% eclipse up here. So which means if you look at it, you need these. Gotta have your glasses. Don't ever look at the sun, or it'll burn your eyes. But there'll be a good use for these on the 14th, October 14th, as long as it's not cloudy. Now we get out to near Earth objects. So near Earth objects are asteroids and comets that come close to the Earth. So an asteroid is effectively a mini planet made of rock, 50 feet across, 50 miles across, some of them hundreds of miles. And then comets are kind of the same idea, but made more of icy materials. Most of them are far, far, far away from us, but some come close to us, and some actually hit us. The easiest way to tell that is get some binoculars and look at the moon. It's covered in craters. Those are all impact craters, all things that have hit it. The Earth has more protection than that because we have a thick atmosphere, so it burns up a lot of the little things, but we've definitely been hit. And you don't see as many craters on Earth because we have vegetation and volcanism, and we have human activity and all these things that can hide the craters. But there's some really well-preserved ones. Meteor crater in Arizona, it's about a mile wide, 600 feet deep. It's amazing. Made by an object, probably only about 200 feet across, the size of that little research station in the bottom. So big enough to, 200-foot thing is big enough to wipe out a city if it hits, because it has so much energy. Even bigger, we found 150-mile wide crater off the coast of Mexico, which more and more evidence certainly looks like it's probably where something, comet or an asteroid, a big one, miles across, probably hit 65 million years ago. And that's really tied into, probably at least part of the extinction event of the dinosaurs, as there's evidence of it all over the planet. But the crater is a pretty big piece of evidence, actually. It's clearly an impact crater. More recently, about 100 years ago, something blew up over Siberia, wiped out 1,000 square miles of forest. Again, probably by calculations, maybe something the size of a Safeway, something like that, as far as a rock. Had that happened over New York or Seattle or London, very different story. We would have lost those cities in that event. And now we keep looking for more. We're spotting more items, more things orbiting, just because we have more tools, more telescopes. There's been more events. There was another event over another city in Russia here a few years ago. No one was killed or anything, but something blew up in the atmosphere and blew out windows, and we can monitor from the ground. And so there's a lot of work to learn what this is. Back to the same thing like we were talking on solar flares. We've identified a threat, just like, in the Midwest, we know tornadoes are a threat. So over the years, we've developed Doppler radar and warning systems and shelters for people and much better ways to predict things. We're doing the same thing with asteroids. So we're sending up missions, we're seeing what they're made of. We're actually firing impactors in to see what comes out of them. We've brought samples back so we can see what's inside of a comet. The OSIRIS-REx mission is on its way back right now, and it's going to get here in a few days. It actually went and orbited the asteroid Bennu for more than a year. And one of its reasons to go there was because this asteroid could pose a threat to the Earth in about 150 years. So we wanted to thoroughly map its gravity field. That way, we're thinking ahead now for our great grandchildren. So they're like, if there's some things we can give them that are tools, let's do it. And it also took a sample out of this, and it's going to bring it back and parachute it down to the Earth. And we kind of think of these asteroids and comets as threatening, but also most likely in the early days of the Earth, that's probably how a lot of the water got here. We're not positive, but at least some of it. So there's probably water inside me right now. I'm 85% water, right? That came from comets and asteroids. So it's what's dangerous can also be life-giving. And they're filled with resources. There's asteroids out there that have like more titanium than we've ever mined. I read once that all the gold ever mined on Earth could fit like in like 2 Olympic swimming pools, something like that, all of it ever. There's asteroids that have all that like right in one spot, if you can get to them. So there's potential for a whole mining economy out there. If we can get that flying into space inexpensive enough, reusable enough, then that opens up all sorts of possibilities. And we can, maybe go build space colonies and be able to more efficiently get the raw materials to build solar power generators that could beam down not free, but clean energy down to the Earth. So a lot of opportunities. Now we move on out through the solar system to Mars. And Mars is a really interesting planet, quite a bit smaller than the Earth, a very, very thin atmosphere, but it has some amazing features on it. This canyon on Mars makes our Grand Canyon look like a ditch. It's gigantic, actually, because it's a lower gravity planet, so things could just get bigger on it. It's got the biggest mountain in the solar system, dwarfs anything on Earth. Actually, Olympus Mons does. It's got a couple moons, but not very big. They're probably captured asteroids. So they're not big enough to have a huge effect on the planet. But this is a really cool picture. This isn't no photoshopping here. It's an actual photograph from the United Arab Emirates Hope mission. And that's the moon Dios. And right in front, it just happened to be right in front of Mars for this picture. So there's lots of different spacecraft around Mars from multiple different countries right now. NASA has 2 rovers operating on Mars. Curiosity and landing these rovers, really a tricky process. This sky crane is pretty sci-fi looking stuff, but it has worked twice in a row. This was actual footage from the Perseverance coming down and landing on Mars. They effectively put a GoPro camera on it. They're like, it was an afterthought, like, we should film ourselves landing. Like, okay, let's stick a camera on. It was like not quite that easy, but and here's a picture taken yesterday from Curiosity. So there's a couple of fresh pictures of you from the surface of Mars. You can see the wheels of Curiosity. It's pretty rocky terrain they're on. But that back there's lots of places on Earth that look an awful lot like that. That's very familiar to me. So, and there's dust devils on Mars and avalanches and tornadoes. But they get windstorms that sometimes cover the entire planet. So very, very different environment. And we have a helicopter up there. We have a drone flying around. And this was actual footage of its first flight. It was only supposed to last for 4 flights. It's on 50 now, something like that. And they're actually using it to scout out the path for the rover. They can kind of look ahead and see better than what you can see from orbit. And they've named this takeoff site Kitty Hawk, because it's the first time we've ever flown a helicopter on any kind of air vehicle on another planet. But Mars did have to dodge one of those comets. We keep talking about asteroids and comets. This was a big one a few years ago, like a 6-miler, and it missed it only by 70,000 miles, which sounds far, but like if that had flown over the Earth, that would have wiped out half of our satellites. We actually had to put all the orbiters there at the time on the other side of the planet at just the right time, so they wouldn't get hit by all the dust coming off the comet. So there's lots of missions on Mars, and the whole goal, we're building towards that idea of being able to get humans to first explore there and ultimately, colonize would be really the goal. So we talked about the asteroids that come close to the Earth. Then there's another whole belt of asteroids beyond Mars, and we have sent spacecraft there. The Dawn mission studied 2 different asteroids, the 2 biggest ones, and there's a couple other missions I don't have on here now. There's one called Lucy that's on its way there, and one called Psyche that's going to be taken off pretty soon. So lots to study in the asteroid belt. Just as we step in towards the outer solar system, just take a second to think about, NASA. You pay for an awful lot of this. Some private companies pay for it, but you pay for an awful lot of it. NASA's budget is less than 0.5% of the federal budget, so less than 0.5%. And by a lot of estimates, we get some pretty big yield back from those investments. But yeah, I can't spend too much time on this slide because people want to ask about all the other parts of it. So let's go. But just so you know, that like every one of these is representing a mission or an effort that NASA is working on. It's huge. And NASA is the National Aeronautics and Space Administration. So I'll talk just very briefly about the aeronautics part. In general, I can tell you it's safer to fly. In fact, much safer to fly because of what NASA does. They have flown, a great example is them deliberately flying an instrumented plane into downdrafts coming from storms to evaluate what wind shear looks like. And we used to hear about wind shear airplane crashes somewhat frequently, actually. Now, thanks to all that NASA research, there's onboard wind shear warning systems that we have a better handle on. NASA has helped with checklists that they used from their skill to help make things better for pilots. And they've done whole efforts that have greatly improved airline safety. They've done a ton of work on supersonic flight. Right now, we're working on a much quieter way to fly a supersonic airplane. So that first A in NASA has an awful lot going on. There could be a whole presentation just on that. So now we're getting out to Jupiter, gas giant, biggest planet in the solar system. And I say gas giant, I mean just that. It's made primarily of hydrogen and helium, just like the sun is. If it had gotten much bigger, it could have turned into a star, but it didn't have enough gravity for that to happen. Average temperature, 258 degrees Fahrenheit, is below zero. Back to remember our scale model, where the tennis ball is our sun, and 22 feet away is a little spitwad that's Earth. At that same scale, Jupiter would be like 116 feet away. So out in the parking lot, maybe halfway across the parking lot, something like that. Wow. It does have, it has several moons, but it has 4 big ones, are the Galilean moons, which were discovered by Galileo when he looked through a telescope. And I can tell you, if you just go out with a simple backyard telescope or even binoculars, look at Jupiter, you can often see at least a couple of them, depending on where they are. It's very cool. You can't see them like this; they're just little white dots, but it's still pretty neat. The Voyager spacecraft in the 70s, both Voyager 1 and 2 flew by Jupiter, just took some amazing pictures. This is the Great Red Spot on Jupiter. It's a storm that's been going for hundreds of years. And when this picture was taken, it was a few times the size of the Earth. Now it's only like 1.5 times the size of the Earth, but it's a hurricane bigger than our planet. And communicating with these spacecraft so far out takes a pretty advanced set of equipment in the Deep Space Network. We have to have dishes and communication on different points around the globe to be able to always have something pointing at the spacecraft. And we're still talking to those Voyager spacecraft, even though they're 12 billion miles away now. At the speed of light, it takes a day to get a signal to them and a day for the signal to come back. It's that far away. The Galileo mission, appropriately named for Galileo, in the 1990s really focused on the moons. Io is the most volcanic spot in the solar system, active volcanoes everywhere. And even though it's so far out in space, it's so hot because just like our moon makes our Puget Sound go up and down from the tides, Jupiter and the moons around it move the entire crust of Io up and down hundreds of feet a day, melting the rock inside and then causing these volcanoes to happen. Europa, similar, except its surface is covered in ice, but we're pretty sure there's a lot of heating inside, and the suspicion is that there's probably a big ocean underneath all that ice that's still being heated up all the time by that tidal activity. Possibly more water on Europa than there is on all of Earth. The Juno mission, Juno was at the time Juno went into orbit around Jupiter a few years ago, was the fastest object humans ever made, and doesn't have any humans on board. But like we've talked before, there's astronauts, the first interplanetary space Legos. So we have Juno, and we have Jupiter or Zeus from mythology, and then very appropriately we have Galileo with the telescope that he used to first look at Jupiter. So those guys are orbiting Jupiter. This is a little picture I took from my backyard yesterday morning, because Jupiter's really bright in the sky right now, and I'm just like, hey, there's Legos orbiting that. That's kind of cool, isn't it? So there's also lots of science, which is more important. And there's a shot from just a couple weeks ago from Io and Jupiter. And back to asteroids and comets again. Couple decades ago, we saw this comet Shoemaker-Levy 9 break into 1 mile sized pieces, and it actually hit Jupiter. And we were able to see it happen. And a year later, it left these scars. So, we kind of looked at like, even though big asteroid events are rare, in a 20-year period, we saw one almost hit Mars, next planet over, missed it by 70,000 miles. We saw one hit Jupiter. Now, we think Jupiter kind of helps us out because it has so much gravity. It probably takes a lot of hits for us. And we think maybe having a Jupiter and other solar systems is critical to having a habitable planet. But still, there's a bit of a shooting gallery out there. So now there's actually an official NASA Planetary Defense Coordination Office, and there's coordinated budgeted efforts. And one of the big effort, a lot of it is tracking down all this stuff, but it's not just tracking it down. And there's a lot, these aren't all objects that are going to hit the Earth, but they're all ones we're paying attention to, at least a couple thousand so far. And we find more all the time, the more we look. But now we actually have the ability we've tested something to do something about it. And last year there was a very successful test called DART, where we went out to an asteroid that wasn't going to hit Earth. It was nowhere near, we couldn't even mess it up. And we actually fired an impactor in, and it was highly successful. We changed the orbit of an object. It was an asteroid, a small asteroid orbiting another one, and we dramatically changed the speed of its orbit by hitting it with something we sent from Earth that had to find what it was going to hit within seconds of the actual collision, going at huge speeds. In that scenario, and it doesn't solve everything, but in that scenario, that kind of a hit would have deflected an asteroid that was headed to Earth, depending on the type of asteroid. So that's kind of exciting to me that the world has gotten together. And again, international effort. The Europeans are going to send a spacecraft to go look at the leftovers to see how it turned out. Saturn, another gas giant. We're getting way out there, 308 degrees below zero. It's cold, takes 29 years of our years to go around the sun. Its rings are just amazing. This is a picture from the James Webb Space Telescope. And those rings are thousands of miles wide and sometimes only tens or hundreds of feet high. So sometimes if you're right on edge from a distance, they seem to disappear until you get to the right angle. And Saturn has quite a few moons. The Cassini mission studied, a very successful mission for years. It studied Saturn and its whole environment. One of those moons is Titan, and Titan's unique because although it's a moon orbiting the planet, it has a thick atmosphere. So it's the only moon in the solar system that has a thick atmosphere. And to find out what was below it, we actually sent a probe down through on a parachute and took pictures. So this is a picture taken from 1 billion miles away of the surface of a moon around another planet. Wow. And again, at the speed of light, it took an hour for this picture to make it back to Earth. So when you see Saturn, or when you see Jupiter at the night sky, that's a half hour away. It took a half hour for that light to get back. Here it's an hour. On the way down, they discovered these are river channels of liquid methane. It's hundreds of degrees below zero. So natural gas, like it exists here on Earth, it's so cold that it's liquid there and it evaporates and it rains. And so if you lived on Titan, you would build your buildings out of frozen water ice because that would be rock. And liquid methane would be your rivers and your drinking fountains. And we're building another spacecraft called Dragonfly. It's going to fly up there and hopefully in about a decade to go explore more. And here's one of my favorite pictures of all time. This is a picture taken from the Cassini spacecraft on the opposite side of Saturn. So you can see all the rings, the sun is perfectly backlighting it. And this is one of the ones where anyone online, I want to point to it with my pointer. See that little white dot? Actually, that's right. Sorry. I'm pointing at the wrong spot. See that little white dot? Yeah. That's us. That is Earth. Oh. We're all in that picture. That's the ultimate selfie, right? We built a camera, we sent it out 1 billion miles, turned around and took a picture of ourselves. So I hope everyone combed their hair that day and everything, because you're frozen in time. Uranus is the next gas giant. It's actually called an ice giant. It takes 84 years to go around the sun. Beyond there's centaurs, another whole class of rocky bodies that we don't know that much about and haven't studied that much yet. Then we get out to Neptune, the last of the big planets, another ice giant, 164 years to go around the sun, 360 degrees below zero. You can see these extremes are happening, and the distances are picking up too. On our scale model, with the tennis ball and the Earth being 22 feet away, Neptune would be 2 football fields away. So we're, here we'd be out in the water somewhere, maybe, or something like that. And we talked a little bit about the James Webb Space Telescope. It's been up operating for about a year now. Amazing, most powerful space telescope ever built. It's designed really to look deep into space and the galaxies that formed billions of years ago. But just like that picture of Saturn, we were able to get pictures. We haven't had pictures of Neptune like this. That's even better than some of what the Voyagers did. And we can see the rings around it because we're looking at infrared light. So that's the freshest picture we have of Neptune from the James Webb Telescope. So there's our solar system. There's our 8 planets, and there's this guy down at the bottom. that we used to call a planet, Pluto, until it got promoted a few years ago because we realized it was a whole different class of objects. So the last time Pluto was where it is today in its orbit, George Washington was 43. So the entire history of the United States would be like, if we lived on Pluto, we'd be coming up on anniversary 1, year 1 of the United States, right? One loop around the sun. These were the best pictures we had of Pluto before from the Hubble telescope, using every bit of enhancement we could get because it's so far away and so small. So we sent the New Horizons spacecraft. Took 10 years to get there, fastest thing we ever sent across the solar system, and it took amazing pictures. We thought Pluto was going to be this boring rock. It's highly dynamic. There's this big, they call the heart of Pluto. It's made of frozen nitrogen. There's just these amazing features, and there seems to be movement and like things that blow everyone's mind because they're like, this is so far out, it should be kind of cold and dead by now, but it's not. It's got a moon Charon, which they kind of both orbit a common point, and so my wife's name is Sharon, spelled differently, my wife in the back corner. And so this is the kind of Valentine you get from me. The Cat's Eye Nebula, the frozen ice heart of Pluto, and Sharon. So I heart Sharon. That's what's on our refrigerator doors. Isn't that so romantic, I tell you? So there's features, there's mountains on Pluto as high as the Rocky Mountains made of water ice, frozen. Picture an ice shard 10,000 feet high. It's just an amazing place. And it's got a blue atmosphere. No one expected that. That was a picture from the backlit from the sun as they flew away, and it had this amazing, amazing atmosphere. So Pluto's part of this Kuiper belt, and this Kuiper belt, so I said when it got promoted, we realized we stopped calling it a planet because we realized it was just the closest to this whole other category of stuff. And so there's lots of objects out in the Kuiper belt. New Horizons went on another 1 billion miles and flew by Arrokoth. That's a much smaller object, but it's the furthest thing we've ever flown up to close with the spacecraft. And then out in the Kuiper belt is Eris, which is about the same size as Pluto. So when we've discovered Eris, that kind of changed the equation on what we call Pluto. So back to our model with the Earth, the tennis ball sun, 22 feet away, the Spitwad Earth, at that same scale, Eris would be, so say I put that tennis ball, I think most of us could picture downtown Seattle. If you went to the aquarium, if you put the tennis ball at the aquarium, a half mile away, you'd put the little itty bitty Spitwad at Coleman Dock at the ferry terminal. So we'll come back to that one last time on our scale model. There's probably another planet out there, probably a 9th planet. We're not positive, but the way other planets orbit around each other, it certainly looks like there might be a big gravitational field out there. It's probably an Oort cloud out beyond that. We can't see it, but we see comets come from it. So we see the messengers coming from this area. And then we kind of get out to the edge of the solar system. Those Voyager spacecraft still operating, still sending back signals, built in the 70s, amazing. And they've gone into what's kind of considered interstellar space. They've stepped outside the sphere of the sun, and they've been able to measure changes in the magnetic field. And they're sending new data after all these years. Things look different out there than we thought. And here's kind of like a big picture of it, So we talk about the sun. So the sun gives us good stuff, heat, light, right? Photosynthesis. It gives us bad stuff, radiation, knocks out power grids. But in the big scheme of things, it is like an invaluable partner because it's out there. There's all these other stars bombarding us with cosmic radiation, and it creates this bubble that is pushing its radiation out, and we see it fluctuate. When the sun is less active, cosmic rays go up on Earth. When the sun's more active, cosmic rays go down, but sun rays go up. And so we're always at this balance. The Earth is deep inside the solar system in this little protected bubble as this kind of cosmic thing happens around us. It just makes our existence here kind of remarkable to me. Kind of getting back to the solar system, let's go back to Eris one time. So Eris, kind of the furthest big thing we know about in the solar system. You might know a couple other, but it's like the furthest big kind of planet type thing we see in the solar system. So last time on my scale model, tennis ball, sun, little Spitwad, 22 feet away on the other side of the room would be the Earth. Eris, furthest thing we know about in the solar system, would be a half mile away, or like the distance between the aquarium and the Coleman Dock, or for us, maybe the Minette Bridge, something like that from here. So just think in your mind how far you'd have to go to put the next tennis ball this size on our scale model to represent the next closest star. And that distance That place is Phoenix, Arizona, 1,126 miles away. The actual star is Proxima Centauri. The actual distance is 4.2 is 24 trillion miles, or 4.2 light years. In other words, the light from the closest star to us takes 4 years to get here. So the scale model for you. So if you think about that, the closest star, the photons of light that leave it take 4 years to get to you. So if I see Proxima Centauri, I don't see what it looks like today. I see what it looked like 4 years ago. It's the closest star. All the other stars are further, some of them much further. Some of the light you see in the night sky took tens of years, hundreds of years, thousands of years, hundreds of thousands of years, millions of years. With our better telescopes, we can see light that took billions of years to get here. You look into the past. There are stars that have been born whose light hasn't made it here yet. There's stars that we see that don't exist anymore because they have since burned out. So we live in the Milky Way galaxy. We can't take a picture of our galaxy because we're inside it, but we see lots of other galaxies around us, and we've been able to really image it well. So a galaxy is a whole collection of stars orbiting a common point. The center of it is a massive black hole. You were asking about black holes. We have a huge black hole in the middle of our galaxy that we've been really able to measure. Everything we talked about today, our entire solar system, is represented by a dot on this screen, so small you can't see it. Picture a dot that's too small to see. That would be our solar system. The next dot over, you still couldn't see it. In this whole galaxy of ours, there's probably about 400 billion stars. The volume of our solar system makes up 1/septillionth of the volume of the Milky Way galaxy. So that's 1 with 24 zeros after it. It's that tiny chunk of it, our entire solar system. Even at those distances, there's things we have to worry about. Several years ago, we got hit by a blast from a magnetar that we later pinpointed to have come from 50,000 light years away. This magnetic blast actually passed through the Earth. It disrupted satellites. It altered our magnetic field. There's nothing we can do to stop something like that from happening. But it really hones in that whole concept, right? Like, we're in this together. We can't stop a magnetar from sending a blast to us, but can we work together on sharing information about it? Can we maybe think about having backup satellites to replace the ones that might get knocked out that are critical ones? There's just all sorts of ways the things we have to face. There's things should be easy to prevent are the ones we cause ourselves, but that doesn't always seem to be the case. But and there's things we can mitigate, maybe deflect an asteroid. And maybe there's things we have to, do an evacuation or have backup plans, or, ultimately have us living on a couple different planets. There's no one to go out and, call for help for these. We're in it together. When I look at that little dot out there that we're in, I look at that as, that's a precious, wonderful little lifeboat sailing through some pretty stormy celestial seas, and we all need to take care of each other. You can't have anyone sink in the lifeboat. You have to work together, and it takes a lot of things to do it. A lot of people that come back from the space station start referring to their fellow humans as shipmates. It's like, yep, we're shipmates. We're on a ship together. So NASA spends a lot of effort looking at our solar system, but also we build our instruments to go out and look beyond, get above our atmosphere, look deeper out into space. This picture, I love this picture. This is the Hubble telescope's ultra deep field. So picture standing out in the night sky and looking through a drinking straw, like just a regular milkshake drinking straw, and think of that little point of light you'd see. That was a zoom in with Hubble. Timed exposure, what can we see out there? They picked the darkest part of the night sky. In fact, a lot of the researchers thought they were nuts to waste their time on the telescope doing this. Zoomed in on it, 5,000 galaxies in that one little spot. Galaxy, 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 each with probably at least 100 billion stars. If you extrapolate that out to the rest of just the visible universe, probably somewhere around 1 trillion galaxies, 100 billion stars each. If you do the math on it, there are more stars in the visible universe than there are grains of sand on every beach and every desert of planet Earth. If you added up all the grains of sand on the Earth, there's more stars than that. So it's kind of overwhelming to me a little bit sometimes. This is, you look out at this. This is Lani Akea. This is something we've measured by tracking multiple galaxies. So there's 100,000 lines in this picture, and those are being able to basically see how they're moving through space. We're able to say at the end of each of those is a big galaxy like the Milky Way, not a bunch of the little ones. There's a lot more little galaxies, but so each one of these, so there are 100,000 Milky Ways, the structure massive across the universe. So if we had an address, our address would be Bremerton, Kitsap County, Washington, United States, North America, Earth, Milky Way galaxy, Laniakea. That would be what you'd have to put on your postcard. And it's beautiful that it's, sometimes, and this is just me waxing a little philosophical though, but when I'm looking at how big all this is, I kind of try to bring it back down to perspective for myself. And, so if I come back down to our nice little galaxy here, and I zoom in my mind back down to our solar system, then I get down to the inner part of the solar system. I get to my favorite planet by far. I get to my favorite place on my favorite planet. I'll take Washington, Western Washington. I'll take the earthquakes, I'll take tsunamis. I love it here. It's just such a beautiful place. And then I zoom in a little further, and this is where I work. I work at UW Medical Center. And here at our Montlake campus, in our Montlake Tower, on the 4th floor is our NICU. And we take care of some pretty sick babies there. And I look at that baby and I'm like, my goodness, it took 13 billion years to make that baby. So much had to happen. We had to have stars form elements and then explode and scatter materials throughout the universe. We had to have those materials gather in the right place and have our star form. Our planet had to form at just the right distance from the star to be in that Goldilocks zone so we could have water. Our planet had to be whacked by another planet to form a moon to put us in a stable spot. We have to be just the right age to still have an active magnetic field. We had to have the right mineral conditions for things like photosynthesis to happen. We had to have the water come in bombarding us. We have to have our sun at just the right strength that it's keeping out the cosmic radiation, but keeping us safe, but not bombarding us at the same time. To me, it's astronomically unlikely for all this to come together. I mean, the odds of us having this conversation are 1 in a quintillion or something like that, in my opinion. If I look at everything that had to go so stunningly right, 13 billion years to make a baby. And it's up to us to finish the deal in that NICU. It takes a lot of people to save that baby. It takes people working together. I work in facilities. We have to make sure there's clean filtered air. There's backup generators. We have to make sure our custodial staff keep the spaces clean. We need social workers that will make sure that there's a safe environment for that baby to go into after it leaves the hospital. We need nurses to teach about skin-on-skin contact and how important that is for bonding. We have IT people that need to make all the computers work, the nurse call systems work, so when an alarm goes off, people get the alert and run to go save that baby. All that has to work together. Plus, we're a teaching and research hospital. So we're not just trying to save that baby. We're trying to learn how to teach people how to save other babies and find better ways to save babies and other people. So all of that comes together. So 13 billion years to make this baby. Up to us to seal the deal, to make sure it gets a chance. And when we get it right, boy, howdy, I think it's a pretty cool thing. And we usually do. So there's a lot of equations that help us understand how the universe works. Speed and energy and light, but to me it all kind of adds up to this. That leads to that, and I think that's a very good thing.
Oh. Thank you.
Thank you. That was wonderful. We have some questions. Are there any questions here in the audience? Yes.
You talked about, I think it was Jupiter and maybe one other as being a gassy planet.
I can repeat it too, Joe.
As being gassy, but then you talked about asteroids and such hitting it. How do you hit gas?
Right. So the question is, if Jupiter is a gas planet, how does anything happen when an asteroid hits it? It's still massive. It's very, very dense. There's just not like a hard surface on it. We've actually sent some probes down, one probe down into it to try to see what we could see. And it kind of just appears to get thicker and thicker, but then it turns into a real mystery down in the bottom parts. I mean, we don't know what we think. There could be like weird liquid metallic things happening down at that because of the pressures are just so beyond anything we can imagine. We just know it's mass and it's there. And like even, and it is interesting though, the fact that it's made of gas, that those asteroids hit and a year later, there's still a scar in that spot, even though there's all this swirling activity going on. So it is a weird concept, but it's not like gas, like you could just go run through it. You're right. You know, it's still a very, very dense thing that doesn't have a walkable surface on it.
I have a quick question though. I think, how many satellites do we have up there now?
Thousands, and about twice as many as a couple of years ago, actually. Question, possibly too many, or at least it's getting to be challenging in orbit, especially now that all these satellite constellations for internet service are getting launched. There's Starlink and Amazon's going to do one, and so it's tricky. Quite a few satellites, actually, thousands.
You're next.
So, when you were talking about Mars, that made me remember how I've heard the Mars has, once was a habitable place, once, you could live there.
So-
what do you know about that?
So the question is, he's heard that Mars was once a habitable planet and that possibly you could have lived there. We really do think that's the case, actually. From our various probes, from the rovers we've had, we have definitely confirmed that there used to be liquid running water on Mars. We have found river channels, we've found pebbles. There's, in fact, I mean, the Curiosity rover is exploring a river delta right now that's dried up. It's all dried up now. There's a lot of frozen water, frozen ice, that's water ice underground that we think might have gotten captured there as the planet cooled, was cooled down. We've checked mineralogy. There's possibilities that some of that could have been good enough for life. Now, could have it been to the point where like we could breathe there? Probably not, but we're still trying to find out. We're still looking. I mean, it's not impossible that there could still be some living microbial life down in the soils or something like that. A lot of what NASA does it's kind of interesting. They're astrobiologists, they're called. A lot of their work is going like up into the Andes or Antarctica or Greenland, to really extreme environments, and seeing what life they can find there, to see like, and basically everywhere they go, they find that some sort of life can survive. So it is very possible that Mars used to support life. We just don't have solid evidence, but we definitely know there used to be the key elements. I mean, liquid running water that you could have drunk, just like I drink out of this glass, out of a river. That used to be the case, a billion or so years ago.
I have another question. He said that we have an iron core. And is that very unique? And you said that it was quite unique to have an iron core like the Earth does. But are there other ones that have that?
So it's not so much, and again, we still have a lot to learn. What's unique about us is not so much the iron core, it's that our planet is the right size, that it hasn't cooled off too much yet. So it's still hot enough to have this dynamo going. We think what happened on Mars is just because it's a smaller planet, so there was all this energy left over from the formation of the planet, but because it's smaller, it cooled off quicker inside, not like the surface temperature, but inside. So its dynamo slowed down. So then it didn't have, and it still has these little magnetic fields around it. So there's still something going on in there, but not a planet-wide magnetic field like we have. So without that, then the sun was able to blow away a lot of its atmosphere, which back to the question about whether we could have lived on Mars. It used to have a much thicker atmosphere. We know that, and that atmosphere has been blown off. But we see huge magnetic fields around Saturn and Jupiter. So there's clearly dynamo action of some sort happening in there. One of our missions for smaller objects, I talked about, there's a mission called the Psyche mission that's coming up. It's going to launch here pretty soon. There's one asteroid out there that we've remotely been able to detect as very, very metallic, more metallic than we can understand. So there's thoughts that it might have been the core left over of a small planet in the early days and got smashed into, and that's what's left. So we're sending a spacecraft there to see it, and that'll probably be the closest thing we can do right now to be able to see what does the core of a planet look like. So there are probably plenty of other iron cores out there.
I think that was wonderful. Thank you.
Thank you, everybody.